So hello again. Tonight we're going to talk about something called quantumistic computing. If you've ever heard of relativity, and then you've heard of things that were related to that as relativistic, this is if you have quantum computer capabilities and you relate that back to classical computers, improvements, extensions, enhancements, and that would be quantumistic computing. That's what we'll talk about. So some people might say, oh, this quantum physics stuff and computers, that's off topic for Broward astronomy, since a lot of things are using computers to do the analysis of what's up in the sky and evaluations of things as the computers enhance themselves into the realm of quantum computers. So I think maybe a bit of a stretch, but I think quantum computers are somewhat related to what's going on. Unless, of course, you want me to start talking about gravity waves again.
Oh, no.
So for those people that aren't that familiar with the aspects of quantum computers, I'm going to start talking about qubits and superposition and entanglement. And if those are relatively foreign, even after seeing this presentation, there's a whole bunch of links at the end that you can go do sort of your homework on. In general, what you're hearing as far as promotion of quantum computers is, sure, classical computers may be supercomputers and they're really, really fast, but compared to quantum computers, they're just so slow. You know, it might take more seconds since the beginning of the universe to calculate something, and a quantum computer has supremacy and it will do it in, 2 hours. There's an asterisk at the end of that, and you have to understand what they're talking about, and then you find out that they're doing an algorithm that has no useful purpose in the practical real world, but they can do it quickly. They can do it sort of accurately, but they don't go for enough runs to really nail the value down. They just ballpark it, and therefore, we've got an answer. Look how much faster we got an answer. That's because classical computers do things in loops, iteratively, and the quantum computer just does a flow, comes to a conclusion. So we'll talk about those two distinctions. But until you learn more about quantum computers than you're learning from, let's say, promotional hype or rebroadcast of existing promotional hype or manufacturers' promotion of it, you won't know what their shortcomings are. But there's links at the end. You can find those out. And as I often say, you'll never know how much you didn't know about quantum computers until you know what you didn't know. So as I was saying, think of quantumistic as kind of a parallelism to relativistic, root grammar words, but not related to each other in the form of physics. So there are additional things that classical computers can have added to them called field programmable gate arrays, where you can define electronic circuits basically by software. And there's nothing that would restrict you from defining something that could be multiple values at the same time, kind of like quantum computers, but they wouldn't require all the things that quantum computers require, which is like superconducting, near 0 Kelvin, critically cooled. And the one that I just learned about 2 weeks ago, which is they're so sensitive to gravitational and magnetic fields that you actually have the equivalent of an MRI magnet associated with all of the better quantum computers. You have to have all sorts of shielding because they're sensitive to extraneous radio, and the individual qubit values are susceptible to all kinds of distortion. So you have to have all kinds of stuff for detecting errors and correcting them. But if we could improve classical computers so they could do some of these quantumistic things, then they wouldn't need all that baton baggage. And if you think back to not too many years ago, the graphics cards had these things called graphics processing units or GPUs. And at some point, the GPUs moved from separate plug-in cards to it's on the motherboard. It's just in this extra chip on the motherboard. And now they're actually in the CPU chip, in the processor chip. So the direction of the technology of computer hardware is, if you find something useful, it first shows up as an add-on board, and then it migrates, if it becomes more popular and useful, to a more common level of it's on the motherboard, like on the main board of the computer. And then if it gets even more significant and you can shrink it down to fit in the actual chip itself, the actual computer processing chip, then it just becomes another embedded thing in the computer chip. GPUs, the graphics processing units, those were maybe about 10 years ago. Well, about 5 years ago, neural networks or large language models, the engines for doing that quickly, called neural processing units, having nothing to do with brain cells, neurons, but neural processing units that do large language models. They started out as add-on boards, and then they became chips on the motherboard. And now the latest generation of CPU chips actually has GPUs, a couple of NPUs, some digital signal processing chips, all in the CPU chip. So that's just a trend of how things go in computer technology. I would think eventually, if we can get the quantum processing capabilities out of the realm of 0 Kelvin and high magnetic fields, if we can make them usable in normal environments, you'll see them first as add-on boards and then chips on the motherboard, and then we now have a quantum processor that's built into the main processor. So when we're referring to quantum and quanta and things like that, here's the simple description of it. Quanta refers to something that's a measurable item. And if you have a lot of them, then quantum. So if I was counting balls for ball bearings, an individual ball would be a quantum item. And if I was counting them up, it would be counting of quantum items. But when you work in physics, the quantum items are electrons, photons, and electrons, they're basically created and trapped, used for various logic purposes, and then released. In the case of photons, they could be light, they could be X-rays, they could be radio waves, different bands of radio waves, mostly in the microwave range because those are small and energetic. But quantum computing is about collectively measuring all of the quanta that you're dealing with. In the case of electrons, it's very common to use properties of these quantum items like spin and charge. Charge not so much because it's difficult to change the charge without it becoming a different particle, but spin, right-hand rule, spin up or spin down, which aren't really spinning and they aren't really going up and down. They're just discernible characteristics that change based upon behaviors. So spin flip is a behavior and spin is a property of a quantum item. So I can delineate, I'm looking at that thing now, I just measured it. Is it spin up or is it spin down? When you put something into the quantum realm and you haven't measured it yet, it can be spin up, spin down, or anywhere in between, and it might actually oscillate back and forth. So when you're manipulating them, you're manipulating in this state where they can be any value between a range, and you're doing computational work on them using operators just like you would in a classical computer, the ands and the ors and the nots and fancier ones than that. And you let the data flow through with its oscillating quantum. And then when they rattle out to the end in a matter of, maybe a few milliseconds, you'll have your converged solution, the conclusion. It'll have all fallen through. If you've ever played pachinko, and I don't know if I'll get demonetized, but I'm not monetizing the channel, but the word pachinko is actually a registered trademark of a company in Japan. It's that thing where you see an array of nails and they let like a ball bearing drop in from the top, and it rattles down through and comes out the bottom. And if you dropped a lot of those, they would rattle around in there, and some would come out one area and some would come out another area based upon their interactions. So I like to think of the flow of a quantum computer kind of like a pachinko machine, where you can control what the individual nail heads are doing.
Yeah, but it's also like a quantum machine because even though you can't predict the outcome of a single one, right, the overall probability. I'm sorry, you were probably going to say that next. I'm sorry.
No, I wasn't. I was just referring to it as much like in a pachinko machine, if you drop a bunch of the balls from the top at the same time, depending upon how you clump them and which pins they like cluster to, and even the tilt of the machine will dictate where clumps will appear at the bottom. And that's just the operators that you're using to manipulate the flow. And a quantum computer is kind of the same thing. If you start with a flow of these flippy things, as they make it through, you have different operators you work on, and that determines where they're going to come out at the end. But the reason why we state these things as we don't know where they're, what state they're at until we actually measure them. What can we measure of them? Well, if we're using radio waves or photons, we can measure the amplitude, sort of how many volts positive or negative the energy is in the particle, the wavelength, the oscillation, nanometers of it, the length of it, or the phase. This is where that sine wave curve is like a little bit shifted one way or the other. And the way we measure all that stuff is through something called the photoelectric effect. Thank you, Big Al, Einstein. But the one thing to remember is the wave is only a wave because we take it as a measurement in time. If we were to make the measurement times shorter and shorter and shorter and shorter, we could actually follow the wave as it moves through an oscillation. And this is something that the quantum computing community just doesn't want to hear about. And then you point out, some folks won a Nobel Prize for their attosecond observations of electrons, where they actually sliced the reflectivity of what the electron was doing enough where they could see the electron get energized by a photon, move outward at a certain velocity, attain a certain radius from the core of the atom of the element, and then come down from there, eject a photon, and then go back to its ground state. So I like to think of it as if you could slice up your measurements, your quantization of the wave, you might see that, well, I can actually follow the amplitude up and down, and I can see where it started and where the peaks and the valleys are, the peaks and the troughs, so I can tell what the phase of the signal is. But once you can do all of these things, then this whole it's nowhere, it's up, it's down, it's both, it's neither. It's like saying the one that I use as an example is if you've ever watched a hummingbird and you just look at it, the wings are a blur. Well, where are the wings? Well, the wings are at some point up and down all the time. No, not all the time. Your vision is limited. If you could take stop motion, short exposure images of the hummingbird's wings, you could actually see them beating up and down. And some of these high-speed cameras actually do that. So whenever somebody says, it just happens in an instant, or it happens all the time and it's all, we can't tell. It's like, why don't you slice up your quantization a little bit further and maybe you can actually tell what's going on. So as I was saying, in quantization, you have something called the time point and duration. Time point is when you started your measurement, and then duration is how much exposure you gave to it. So if I were to do an exposure that was long enough that it actually encompassed a complete phase reversal, then I would get an average of that waveform. But if I can get a really short time duration, now I can actually see the amplitude changing over time. And as I mentioned, hummingbirds' wings, and also mentioned that, attosecond measurements of acceleration, deceleration of electrons. So what's a blur to some, what's indeterminate to some, is actually determinate to others that can measure time in smaller slices. So now that we've got quanta and quantum defined, a quantum computer, the design of your quantum computer will dictate what kinds of quantum things you're working with, be it electrons or photons. You need some means of transitioning from classical computer data to quantum, and that's superpositioning. That's how you instantiate one of these qubits, and it starts doing its, I don't know what it is until I measure it. But if you want to do what is known as entangle them, there's a thing called a Hadamard function where it literally says, if I know the state of this qubit and I do a entanglement with another qubit, then if this qubit is a one, not a one because it's constantly moving, if I do a quantization of this qubit and it turns out to be a one, and I initially defined the other one by a Hadamard function to be a zero, then if I flip the one to a zero, the zero becomes the one of the other one. So it's a direct coupling between the two. You can actually do that in software. You don't need a quantum computer to do that. It's simply if then else and a computer. But that it's not looping, but it is conditional processing. Now, once you've got something entangled and it happens to be a quantum element, then you can perform logic operations on them like and, or, not, a whole bunch of different kinds. And then in order to read them out, in order to take it from the value to a unique one or a zero, you need to detangle them. So you need to separate them back out so you can read the individual qubit by measuring it. The transitioning of your classical computer digital data into instantiated qubits, entangling them, doing logic operations on them, detangling them, and then transitioning the data back to a zero or a one is referred to as a quantum circuit. And if you ever start looking at some of the videos at the end, you'll find that they talk about creating your quantum circuit from some algorithm. You start out with something mathematical, and then you have to translate that into a quantum circuit. Once you have your quantum circuit defined, now you need to map that onto the particular kind of quantum computer that you're going to be running it on, or a classical computer where you're going to be simulating it. They do make software that simulates quantum computers that instead of paying money to run on real quantum computer hardware, if you have a commercial account, it costs you real money. You can get a free account where you submit it to a queue and they'll get back to you when it gets run. But what it's really about when you measure something, when you quantify it, when it comes out the far end of the process is it's really just range values. When you want, remember me talking about the photoelectric effect, when the photoelectric effect is implemented using an analog to digital converter. The analog to digital converter measures a voltage. Remember the waveform? As the waveform comes up, it measures the voltage at that point and says, if the voltage level is this, we'll call that a 1. If the voltage level is this, that's actually a negative value, and we can't have negative binary values. So what they do is they scale it up and say, if it's this high number, it's a 1. If it's this crossing 0 low number, that's a 0. So when they're talking about quantum computers and them having this spin up, spin down, and they're anything, and you can never tell about it, at the moment when they quantify that, they do actually take whatever that range value is, wherever they catch it, wherever their time point is, and if it's kind of up this way, it's a 1. If it's kind of down this way, it's a 0. And that's how they convert quantum qubit observations back into the 0 and 1 digital world, is by ranging. A quantum computer consists of multiple of these things called qubits, and they support superposition and entanglement. And then we need some way of getting the classical computer bits to becoming qubits, and that's modulating them into radio waves typically. And then we entangle them. So we now have a series of source value streams of qubits. And when we flow that stream of qubits through these logical operators, that's processing. And then when they come out the end of the multiple stages of processing, we need to convert them back into zeros and ones. So we use analog to digital converters to do that. And the results, the readout, is the output. It may be quantum computers, but from my knowledge of computer architectures, that's a lot like a classical computer. You have input, processing, and output. So if you were to take a quantum computer and break it apart into input, processing, and output, and you can map what the quantum computer is doing that's unique back onto something that a classical computer can do, you now have quantumistic computing on a classical computer. So the things you want to be able to do is superposition, entanglement, and these functions, these operators. So if I want to make something superposition, instead of it being a binary up like a 1 or 0, if I can make it back and forth, or I can take the value and spread it across a range of storage locations, I now have something that is multi-stable as opposed to monostable. Monostable being it's a 0 or it's a 1, it's definitive. But if I stretch that across a range of values, much like that qubit does before I measure it, it's a series of high number positive volts and low number negative volts, it's in that range. If I just put values out for that range, I can now have the equivalent of superposition on a classical computer. And then entanglement. Entanglement is just a way of saying, I want to take two sources, 2 qubits, and I want to entangle them or make them such that when I affect one, it affects the other. I don't have to look at the other one. I just know that when I do this to that one, I know what's going to happen to this one. In a quantum computer, qubits need to be close to each other. Otherwise, we have all kinds of error effects that will take place. In a classical computer, you don't have such a thing. But also, you don't have a single instruction in the hardware of a classical computer that will do this entanglement for you. But it's very simple with a couple of instructions to entangle 2 memory locations or 2 of these qubit value arrays to be referencing one another. And they're
Isn't
actually
it just an exclusive OR?
no, because that would flip it, and that would say what one state is versus the other. In a quantum computer, if you have something that is up, you don't necessarily know that the other one is down. So they're not polar opposites of one another. You can have down, down, up, or up and down, and they can both be entangled. So it just means that when I affect one, whatever the value of the other one is, it's flipped. You might say, well, that's just a not, 0, 1, 1, 0. It's a little more complicated than that if you put in superposition at the same time. So it's like I have an array of values and they're entangled. So the actual change to the values can take place not over just one bit, but take place over an array of values. But there actually are instructions intrinsic to current computer architectures that will do those kinds of things. They can manipulate an entire array of things at the same time. They actually do it in parallel. Those are for string and video processing. If you're doing an entire row of a video display, then you need something that can process the entire row as one time. And so there are dedicated instructions, SIMD instructions that are specialized within CPUs. Both the AMD and the Intel processors have these for manipulating matrices, and they do it very quickly. If some of the people out there promoting the uniqueness of quantum computers actually knew a little more about the capability of current classical computer processors, they might realize that some of that quantum stuff could be implemented with classical computers. So this one will draw down upon people's experience over the last 20 plus years. Ever heard of fuzzy logic? There was this feature that was going to be in every device around your home. Everything was going to have fuzzy logic capability. The one that was promoted most was vacuum cleaners. In order for your vacuum cleaner to do a much better job at vacuuming up stuff, your vacuum cleaner would have somewhere within it fuzzy logic. Fuzzy logic is just referring to, instead of things being 0 or 1, true, false, yes, no, it can be kinda 0 or kinda 1. And the best way to describe that about a vacuum cleaner is the suction of the vacuum cleaner, instead of the motor being off and on, the motor could be variable speed. And based upon the amount of suction resistance that the vacuum cleaner was getting, they could vary the motor speed through a range. It's not just on or off. So that was fuzzy logic in vacuum cleaners. You don't hear much these days about fuzzy logic, but the range values of fuzzy logic are very reminiscent of superposition of quantum computers. It's not just 1 and 0, it's anything in between. And you don't know until you actually do it. The potential is for quantum computers to go the way of fuzzy logic. All we need to do is just get their size down, their complexity, their cost, their reliability, their adaptability to more applications, get rid of the critical cooling for 0 Kelvin, and then you would have a quantum computer that could just be another feature of existing computers. But I'm not holding my breath for that to happen soon. The other thing is, people might believe that superposition is something new to quantum computers, and it doesn't exist elsewhere in the mindset of human beings, and that's just not the case. Superposition comes from mathematics. It's actually a subset of something called Quaternions. And Quaternions are used by every one of those drones that are out there flying around. It just means that if you have a vector, a motion vector, the motion vector has more than just a direction and a velocity. It can change in 3D. But since it can rotate as well as changing position in 3D, that actually gives you a fourth dimension. If you learn about large language models and artificial intelligence, they use linear algebra, and therefore the math uses superpositioning without even getting into quantum computers. And it turns out that if you have two of these vectors in either linear algebra or quaternions, if you have two vectors and they're separated by 90 degrees, they're so far separated that you have a definitive result. In other words, it's yes, no, true, false, 0, 1, based upon the separation of those. But 90 degrees is not what you are required to have. You can actually make it 89 to 91 degrees. And there's actually a lemma, a mathematical lemma called Johnson-Lindenstrauss. And I have a link at the end. But what that says is anytime you're going in to make these mathematical measurements of things like, I don't know, qubits, they don't necessarily have to be directly up or directly down. 90 degrees, 180 degrees, actually, opposition with 90, 0, and negative 90. But in the realm of quantum physics and quantum computing, they have this notation called Bra-ket, or bracket notation, where something might be spinning this way or spinning that way. They're polar opposites. And then you can add to that a probability, which is the value range between the two. But that's just two parameters. Math and quaternions have, for quite a long time, supported 3 and 4D superpositions mathematically. So they can support a lot more variability than what quantum computers can support. So when you talk about superposition, and it's up or it's down or it's somewhere in between, but okay, that's just two dimension. What if it was moving the other way? What if I had two photons and the spin was in a different phase? It was spinning at you as opposed to spinning up or down. You'd actually need another vector to calculate that. And you can extend math to cover that. You can extend classical computers to cover that. You can't extend quantum computers to do that because they're just up or down. So existing classical computers have something called a neural processing unit, or an NPU. This is the artificial intelligence coprocessor, and they can actually take essentially matrix values from linear algebra models and crank those through these NPUs and come away with a conclusive value. And they can do that for 8, and some of them can do it for 16-bit 3D visualizations. And whenever you are playing a video game, a lot of that stuff is just taking place. So some of the things that people say are unique to quantum computers actually are just a confined subset of the actual math that's possible with classical computers that have processing units built into them. So here's something that is different between the two types of computers. A quantum computer is kind of a top to bottom flow. You start your qubits at the top, you run it through modifiers, you might do some Boolean changes and come away with a decision branch, and then you come out the bottom with one or more answers. It's just flow, done, end of run. Now, if you want to optimize things, you have to reset everything and run the flow again and maybe get a more optimal answer. In the case of a classical computer, it can also do flow work. But the other thing it can do is iteration. So we can come down and then decide to do something. Oh yeah, I need to go back and do that again. Now I've got a new value for it. It can take the data that it created in processing, roll that back up to the top and come back down again. This is something a quantum computer has no capability of doing. It can't do iteration. If you want to do iteration on a quantum computer, you run the flow front to back, come away with values, adjust your programming, and then run it back through the top. And every time you do that, all of the conversions from classical to quantum, quantum to classical have to be done again and again. Whereas in a classical computer, it's just additional iterations. Iteration is something that classical is touted as being a shortcoming of classical computers because you have to iterate things. Well, I think if under certain circumstances, if you had the mathematical operators, the matrix math going on, you can do all the flow stuff of a quantum computer, but you can also do iteration if it's needed. So let's talk about the performance of the two. When you're talking about a classical computer, they are very much faster than a quantum computer, but they iterate. They go around the loop multiple times. But if a classical computer can do that, why, what's the quantum computer doing? How fast does it go? Well, remember, the first thing you've got to do is convert your classical bits into quantum qubits. And if you're doing that, that's going to be slow because you have to actually emit photons or emit radio waves or emit electrons, put them in ion traps, and those things can take milliseconds. Whereas the gates switching on a classical computer, those can work at the femtosecond level. Now, milliseconds, nanoseconds, picoseconds, femtoseconds. So a thousandth of a thousandth of a thousandth of the time it takes a quantum computer to cycle. A classical computer runs at about 2.5 billion instructions per second. A quantum computer runs at about 25,000 quantum clocks per second. Quantum computers work on qubits. Qubits is one value. When they enter it, it's one value, 0 or 1. When they bring it out the back end, it's one value, 0 or 1. A classical computer can work on wide values. They can work on higher fidelity values, 8-bit, 16-bit, up to 256 bits in one instruction time. So quantum computers may be faster algorithmically because of their flow, because they can take on multiple values at the same time and they sort of funnel to the bottom, but that's in a single run. They don't support iteration, so you have to modify, you have to do what is known as optimization. You have to take that output, see what you need from it, put it back into the beginning and run it down again. It's kind of like, I guess you could say, running something through a sorter. Back in the day of punch cards, you'd take a deck of cards, and you'd say, I want to sort on this column. You'd run the deck through and it would sort out all the cards to the other columns, and then your one column. And you say, now I want to sort the cards from here plus the next column. So you'd change it and then you'd run them through again. And you keep doing that until you got an optimal result. Same thing with quantum computers. When they talk about a quantum computer being so fast, that's for one run. That's for one pass. The moment that you say, okay, now what does it take to optimize the result? Depends upon how many times you run it. With a classical computer, it runs essentially N-complete. N-complete, the letter N. So a quantum computer runs an approximation of an optimization, and you stop doing runs when you get something that's close enough for whatever application you're going to do it on. A classical computer, if you're looking for a targeted minimum value, you just let it run until it comes up with the answer. So if a classical computer can do some of these quantum tricks, then a classical computer would be able to do all that quantum supremacy stuff and much faster. So you talk about classical computers as being a brute force method. You have to iteratively do all the possible values, and that's what makes it inferior, because it takes too long to process all the possible values. Well, quantum computers don't run through binary ones and zero values. They run through a range of non-deterministic values, and depending upon the sieve you run it through of logical operators, it may produce a result that you're looking for, or it may produce a result that you can't use. And if it's a result you can't use, you have to go back and modify your algorithm and try it again. So that, to me, is iterative. And given how long it takes to do that, that's a lot more brute force than a classical computer. So if you have an algorithm that you finally optimize the algorithm, the quantum computer has done its work. If you have an algorithm on a classical computer, every time you have new data, the data doesn't change the algorithm. The data flows through the algorithm, comes out the other end to a conclusion. So which one is more brute force? I like to think of it as a quantum computer is like you had a fire hose with water in it and you just run it through the process. Whereas a classical computer is you have a fire hose that you're taking one drop at a time out of the fire hose and processing them. If you have more processors, more cores, then now you can process more at a time, but end result is you're processing all of the water coming out of the fire hose, not just a portion of it. The other thing that a classical computer can do is what is known as end-to-end traceability. If you have an algorithm that you're running data through and you have a branch decision, if it's greater than this, then I want to do that. If it's less, then I want to do this. So you have a decision, a branch. Well, if you just let all those decisions occur, you'd get a value out the bottom of your decision tree, but you wouldn't know where did you make all your decisions. At what points did you go left versus right? You can record that as intermediate results on a classical computer. On a quantum computer, you don't really have that capability. There's no ability to store intermediate results and then go back and look at them. Because if you did that, you would actually create noise in your quantum computer, and that would increase the probability for errors. So classical computers, you can store intermediate results and then see how you got to where you did. Quantum computers, you have to just get the end result and then keep iterating your algorithm and then running the data back through again. So if I wanted to take the quantum computer and break it down into its individual components, I'd start with my qubits. If I wanted to make a quantum computer that was inexpensive to build, I'd have to pick, well, what kind of qubits do I want? I don't want electrons and ion traps because I need magnetic fields and it takes effort to do that. I don't necessarily want to use lasers because lasers are expensive. I don't want to work in the infrared or ultraviolet because I can't see that. But if I was able to use, let's say, a low frequency radio photons, now I've got something that's easy to contain and I can manipulate it easily. And the sampling rate would be at the megahertz level. So individual quantums would be processed at the certainly kilocycles per second or kilohertz, but your upper limit would be megahertz, not gigahertz, just megahertz. And if I wanted to increase how well I knew it was a 1 or a 0, I could improve the number of bits in my analog to digital converters, so improving my precision, my quantification. But if I did that in a classical computer environment, I wouldn't need any superconducting or critical cooling. I wouldn't need to do microwave guides to shield things. I wouldn't need an MRI magnet, and I wouldn't need low noise filtering. It would just be a series of stored arrays of values. Now, superpositioning. In a quantum computer, superpositioning is just a range from what I call 0 to what I call 1. You can actually do that in a classical computer. You can have an array of values that are in a range, and then you can process data on every value in that range. And it's easy enough to do with vector processing to do chunks of that And if you extended the instruction set using a field programmable gate array, you could actually do your entire range of values as a parallel operation, a single clock operation. But it would require changes to the hardware. The amount of time it takes to essentially flip the values in a classical computer is either picoseconds or femtoseconds, but it's milliseconds for a quantum computer. And the output and converting it back into something that's usable by a digital computer is, once again, sampling at a time point. And once I take it out of that non-deterministic, the hummingbird's blur effect, and put it back into something that's classical as a 0 or 1, it's no longer flow-based, and now I can process it with a classical computer. So entanglement. How do I entangle two qubits? You'll find a thing on a quantum computer called a Hadamard function. And what this is going to do is take two qubits and entangle them. So whatever the value is on this one, when I entangle it with this one, that's the relationship of the two. If I flip one, the other one gets flipped. But I don't know what the other one was when I started. I just entangled them. If I were to do that with a radio frequency signal instead of a qubit, what I'm essentially doing is adding the two radio frequencies. So I'm taking the peaks and values of the two signals and I'm adding them together to come up with a new signal value. That's entanglement. But in a classical computer, if I wanted to entangle two values, it's literally, I could come up with an instruction that says, I've got a value here, I've got another value here, they're now entangled. And they could be anywhere in the computer's memory. They wouldn't be limited to, a specific distance apart. If I entangle those two, and I do it as a radio frequency, then I have to deal with all the waveform adding of cancellation and attenuation and amplification and the phase offsets of the two. But if I do this as digital values, now I have something that's, they're related, they're coupled, but they're still two independent values. So I can separate them back out. It's very much like if I had two photons that I entangled and one was red and the other one was green, and then I entangled them. When I detangled them and I got one value or the other, I could certainly tell if it was red or green. But if I'm merging two signals together that are close in frequency and wavelength, I don't know which one I started with. There's no ability to get back to the beginning. So the processing section of a quantum computer versus the classical computer. A quantum computer will have a limited quantity of stages that it can enable and select what it runs, what operator it runs. The functions are defined at quantum computer design time. So if, let's say we have and or not, and maybe XOR and a bunch of other things, then whenever I design that computer, that's the functions that are available to me. And if I wanted to add a new one, I'd have to go back to the computer design of my quantum computer to add on a new kind of operator. But there is another kind of function called a Toffoli gate. Now, all this really is a typical two-input gate that has another couple of inputs, and the other inputs are actually used to say, are you going to be, what kind of a gate are you going to be? Are you going to be an AND, an OR, carbon copy, a NOT, an XOR? So you have four different things that this function can be, and then you can take the two inputs and come away with your outputs based upon that. So it takes basically building blocks of these functions, and you can repeat them like cookies. So I can have rows of Toffoli and columns of them, and then I can just go in and program my quantum circuit for which one of these I want to do what function. So it makes it uniform. So I'm not stuck with, at the third row, there's a NOT type gate. Well, I can make any of them a NOT type gate. But in the case of classical computers, all these functions are implemented in software. So I can make any of them do anything just by changing the programming of the classical computer. Whereas with a quantum computer, if I want a new kind of operator, a new kind of function, it's built into the hardware. once Toffoli gates run out of new and different things for it to do, it's time to go back and design it again. So what kind of things, what kind of processing functions would you typically find in a quantum computer? I'm not going to go through all of these individually. I'll just mention you have the normal Boolean logic kinds of things. The first one that seems weird is swapping. I mean, it's kind of like a modified XOR, but you're swapping the two values. And then there's a controlled NOT, which is a Toffoli gate. So you're changing what function you want the gate to perform. And then there's the simple negation. But normally, instead of that being separate, it's rolled up into other sorts of gates. If I'm going to be manipulating my don't know what value it is qubit, it's going to flow through all these gates and come away with a new value after it gets modified. But the one thing that a qubit can't do is multi-bit operations. In a regular classical computer, I can do add, subtract, multiply, divide, shift, and rotate. Those are not the kind of operators you'll find on a quantum computer because you're dealing with qubits, not values. This one I found a little unusual. It's something called process reversibility. It turns out that the way that gates work in a computer, classical computers or quantum computers, I put a value in, it goes through a gate, changes, comes out the other side. If the value changes, then I've lost information. So if I put in a 1 and it comes out a 1, I haven't lost any information. If I put in a 1 and it comes out a 0, something had to become a 0. And what happens is you have to have energy dissipated or gained. So if it goes in a 0, comes out a 1, I had to gain energy. Goes in a 1, comes out a 0, I had to lose energy. In the case of classical computers, this is just waste heat. Not too much attention is paid to it. I mean, sometimes they'll try and find ways like these Toffoli gates to conserve that. So they're looping the output back to the input. So if I put a value in and it comes out, I can take the value that was out, put it back in, and get my original value. By doing that, there's no loss of information. There's no waste heat. This waste heat in a quantum computer actually produces instability, which means it can make the quantum computer less reliable if whatever Boolean logic operation you're doing is not reversible. So if I do something as simple as a NOT, I'm actually producing waste heat. But in a classical computer, you don't pay much attention to it. But in a quantum computer, that can actually induce errors because of the waste heat. If I have something like a quantum computer that isn't reversible, I have reliability problems. If I have something that is reversible, I've actually improved the reliability of the quantum computer. That's not really a requirement until you get to very large scale classical computers where now you have enough gates in a small enough area that waste heat starts to be a lot of heat to be dissipated by, liquid cooling or fans or something. So if you just take the things that they learn in quantum design and you apply them back to classical computers at these very large scale integrated circuits, now you can make them use less power, producing less waste power. So that's something that classical can learn from quantum. Now you've taken your qubits, you've run them through your functions, and now you want to produce an output and convert it back to something that a classical computer can use. You're taking your entangled superposition particles and you're essentially exchanging them out so that they're no longer entangled. You've separated them. And now you want to get it to a Boolean 0 or 1. You use an analog to digital converter, and it'll take something that's kind of this, mostly this, or mostly that, and kind of that. And it'll pick this range means 1, this range means 0. But it could be anywhere in between there. So if you were to look at your answer and say, is that really a 1 or is it predominantly a 1? You would go from a single value to actually maybe an 8-bit value, which is the value that might have come out of your analog to digital converter. So is it really 0 and 1 or is it somewhere in between? Think about the hummingbird wing. This is another fascinating aspect of quantum computers is you can simulate a quantum computer on a classical computer. There is software for saying, I've taken your quantum computer algorithm design And now I'm going to run that against a classical computer where I have function libraries, where the software actually tries to do what the quantum computer is doing. But what they found out was they had to go in there and debilitate the simulations. Because if you run this on real quantum computer hardware, it has to deal with things like noise, heat, things like that. And that destabilizes things. So you have to have error detection and correction. If you're simulating it on a classical computer, those don't exist. So to make the simulation on the classical computer have all of the downsides of the quantum computer hardware, the simulation has to have these foibles in it to create noise and detect noise and mitigate error correction of, generated by noise. So if you just take that out, the classical computer would be running faster. But you want to make it simulate the real world of a quantum computer, so you debilitate the simulation. I just found that to be a little weird. So there are actually presentations out on the internet about practical quantum computer use. So you're, let's say, in the financial marketplace or the pharmaceutical marketplace, and you have some mathematical construct that represents a financial model or a next generation pharmaceutical you're trying to create, the molecular structure of it. You know what that is. How do I get that into a quantum computer? Well, the first thing you have to do is learn a lot about the math involved in quantum computers, the physics and the math, the algorithms associated with it, because you're not going to be able to take just the money model that you came up with that you might actually have a flow chart for. You're going to have to convert that to something that can run as a flow, top to bottom flow, that then you'll find out what your intermediate value is. You'll plug it back in and you'll run it through again and again and again until you get as optimal as you expect. But even if you convert the algorithm to something that looks quantum, it may not work on the kind of quantum computer that you have access to, because the number of stages of functions or the functions themselves may not be available to you. You have to take your algorithm, map it to the world of quantum, and then take that quantum circuit and map it to the actual quantum computer that you're going to be applying it to. And if it's large enough, then when you go to make references between one qubit and another, if they're too far away, you may have to essentially boost or swap the qubit states across your mathematical array. And this is called swapping. There's another form of it called Pauli, the physics guy, twirling. And it's essentially if you get a qubit from one side of your quantum circuit and you want it to reference something on the other side and go through a function, you have to kind of get it boosted along the way so that it doesn't induce errors. Classic computers don't have this problem. You can reference anything anywhere in memory, and it's just like as if it was local. So what if we wanted to make a hybrid, a quantum-assisted classical computer? Someday down the road, you might be able to enhance the capabilities of the existing matrix instructions, the SIMD instructions, or you might take a neural net processing unit, but probably more likely you'll take a field programmable gate array. This is essentially an array of logic gates where you can go in with software, kind of like those Toffoli gates, and say, these gates do this, and these gates do that, and you pattern an algorithm into that array of gates. You put data into it, you let the gates run, clock through, and then you get the data out, and then you can analyze it, kind of like the flow of a quantum computer. But instead of processing individual bits, you can actually process values. So you can tie multiple of these gates together where each gate is a latched bit. And if you wanted to have an array of 256 bytes, you can now do all possible values. So it's kind of like freezing the hummingbird's wings, because you can now say, it's not up or down, I can see any value in between. So the FPGA, the field programmable gate array, would allow you to do that. And because FPGAs are essentially broadside repeatable. I can have a circuit board that has multiple of these FPGAs, and I can wire them together, inputs and outputs. I can actually create wider than most quantum computers today because I bought an inexpensive FPGA that had 20 plus thousand gates in it for $34. And that was an entire circuit board with USB connectors and power and all kinds of stuff on it, connectors for like HDMI and audio and video, and then the FPGA, which is one of the parts on the board. So they're relatively inexpensive. And when I do this with an FPGA, they're already reliable enough hardware devices that I don't have to worry about stability and error correction and detection. I just flow the logic pattern through it. So not only does an FPGA have these gates, depending upon which brand and model of FPGA you buy, you can actually have digital signal processors built into the chip. You can have phase lock loops for doing clocking. You may have specific support for audio, radio, video, signal processing. The FPGA may actually have its own microcontroller associated with it. So you can do loading of data, run it through the FPGA, take the outputs, and produce it, as a result. And to that end, they have all sorts of input-output buses and connections. So you can take in audio and produce audio out. So you can have something that sweetens your audio, or you can have something that produces test patterns of video data. They're now sophisticated enough that if you wanted to make a little tiny game computer that had a display, you could actually make all the controller inputs and the display outputs with a single FPGA and its microcontroller. The instructions that go in the FPGA, those can be loaded from local memory, or they can be stored in flash memory associated with the FPGA itself or off board from it. So much like a quantum computer, you'd load up the FPGA with your circuit, and then you would run it through, take the results that come out, examine that and see, is it optimal or not? If it's not optimal, you can run it back through with different parameters, and it would be running internally at the billions of instructions per second, but externally at the millions of instructions per second. So this would be running essentially faster than a quantum computer if you take into account all of the front-end loading and the back-end and the error correction you would have to do that you don't have to do anymore. So if I said I wanted the best possible FPGA and I wanted to make myself a quantum equivalence, a quantumistic computer, I can get one of these FPGAs that has 10 million logical gates in it. And then I could take those 10 million logical gates and break that down into 8-bit values, store 0 to 255, 256 values. And then I could group those together into bytes. And I would create essentially 256 qubit value. And I would still have enough gates left over to implement some of the logical functions after that. So I would load a value in, I would run it through with one clock time, and then I would get my readout. And I could iterate on that using a classical computer. The conversions for quantum, from digital to quantum and quantum to digital would not exist anymore because the values are all there and they're all digital. So it's like having a 4096 qubit quantum computer plus all of the operator capability without all the critical computing, critical, 0 Kelvin cooling, the superconductivity, the MRI magnets, and not needing additional qubits for redundancy due to the fragility of it all. And I could make a regular computer with an FPGA that fits on my desktop. And if I wanted to store intermediate values, the FPGA actually has memory associated with it. So at any point along the way, I can say, store that out and keep going. So I'd have traceability. But if I wanted this to be wider, I could actually go beyond just one FPGA to multiple of them. And if I get a solution and I want to shrink that down, I can put that on one of these super scalar CPU chips that's the size of a playing card, and now it's all built in. So here's a little bit of computer history. Originally, computers used instruction sets called complex instruction sets, or CISC. This is where a single instruction could do a whole bunch of things at one time, but that one instruction would take like 6 or 8 clocks to run. So the performance was not uniform. It would go slow, fast, fast, slow, slow, fast, fast, slow. Then along came these things called reduced instruction set computers, or RISC, RISC. And what they would do is assure that every instruction clocks at 1 clock. So you have a uniform performance. It didn't speed up and slow down as it ran. But as the RISC processors started to say, well, this is why it's good to do that, the CISC processor architectures would pick up all the good stuff like more registers, faster caches, things like that, and just add that to the classical computer. So the classical computers started to be marketplace equivalent to RISC computers, and that competition continues today. So the same thing could be said for quantum computers. If classical computers can pick out the good bits, the good stuff that the quantum computers do, and then implement that on classical computers without all the baton baggage of the quantum computer, now, you might have thousands of qubits and hundreds of stages on a classical computer. That would probably be a cheaper computer than the quantum computer, because you don't need all the other stuff. So that would increase the motivation of the hardware manufacturers of quantum computers to, how do we get more qubits? How do we make these things run faster? How do we add more operators to them? How do we deal with all of the destabilization from noise, heat, radio frequency fields, magnetic fields, gravitational fields? And the answer is you can't, because they're physical limitations. So the history lesson is, if you know how CISC basically maintained its dominance against RISC by robbing the best bits and ignoring the baton baggage, and that battle still goes on today with like ARM processors versus x86 and x64 processors, the entrenched marketplace will find a way not to be displaced. So I think it's unfair, but there are financially oriented articles out there that are saying that quantum computers are the biggest scam that's come along in high-tech technology since fusion, or even cold fusion. And I think that maybe that's being a bit harsh with it, but also, if the only things that a quantum computer can do, the classical computers cannot do, is superposition and entanglement, what if all of a sudden you were to teach classical computers how to do these two things without all of the baton baggage of quantum computers? And what if we could do it at the broad scale of the matrix instructions that are already part of classical computers, the SIMD instructions, and maybe implementing even more capabilities, either more qubits or more functions or more stages, using bigger FPGAs. Eventually, you're going to find that, we'll just implement that as a coprocessor and then embed it in the CPU. And that's how classical computers will maintain their dominance against quantum computers. So the things that quantum computers define as their superior capabilities are actually just defense mechanisms for their Achilles heel. They're physically large, they're very expensive, they have a limited number of qubits. I think the most I've seen so far is a little over 1,000. They have a limited number of logic stages, maybe 100 or so. It requires a full rack classical computer just to do the input and output for the quantum computer, and to maintain all of the supercooling and things like that of the quantum computer. And you require all sorts of chillers and pumps and dissipators and such to stabilize the qubits from heat sources. And you know that plumbing. I actually did a deep dive on the plumbing that you see in a quantum computer, and what's with the curly cues, where the plumbing pipe comes down and it goes around and it goes down further. Well, first of all, those aren't plumbing pipes. Those are radio frequency waveguides, and inside them, to isolate the waves, the photons from being interfered with by the heated metal of the conduits of the pipes is PTFE tubes, Teflon tubes. And the Teflon, when it gets really cold, has a different expansion, contraction than does the metal tube. So the way they solve this is they'll either put a bend or they'll put a loop, pigtail, in the individual line. So if you've got 1,000 qubits and you've got 2 control lines for each qubit, you've got 3,000 of those plumbing lines that you have to deal with. That's essentially something that will always be a bottleneck financially and physically to a quantum computer. And then quantum computers, in order to be stable, have to have this concept of reversibility to deal with the information loss heat. And classical computers don't have to deal with that, at least not yet. And then there are people that when they watch this video, they go, you simply just don't understand quantum physics or quantum mechanics. It's like, maybe, maybe not. I do have a comprehension of computer architectures, and I have worked with hardware engineers at the computer design level and digitally and analog. So I know about critical cooling. I've seen other physics and other projects that need critical cooling, like the James Webb Space Telescope's imaging chips. I know about gravity wave detectors and interferometers that need isolation from magnetic fields and vibrations and gravitation and those sorts of things. So I understand that. I know how to map signals from digital to analog and analog to digital, how to do that. I've seen purpose-built, very large-scale semiconductor chips being made. I've seen the software used to make those programmable design chips. A quantum computer, the bigger ones, actually require a large warehouse to contain them. Not just the computer itself, not just the computer plus its rack of classical computer, but all the back-end stuff that they normally don't show you. The MRI magnet, the pumps needed to keep the liquid helium at near 0 Kelvin. If you just see that cylinder and think that's the quantum computer, no. That's just a small piece of it. And inside that cylinder, all the way down at the bottom of it, there's a little chip that's like half the size of a poker card. And that's the actual quantum computer. But you need all this baton baggage, all this back end stuff just to make that work. Plus, you need teams of mathematicians, quantum physicists, and technicians to keep it all operational. If you needed all that many people to run your laptop computer, you'd never own a laptop computer. Think back to the days of the mainframe computers that were doing business applications. Yeah, you needed all that stuff. You don't anymore. So my response to them stating, I just don't understand is, I know that in technology, anytime you have something that you're doing and you can perform something that's a role equivalent of it, whenever it is cheaper, smaller, faster, uses less power, and offers a broader marketplace, it will displace the prior implementation regardless. And quantum computers have no defense for this. The best way to mentally think about this is when I first got out of college and was working with real-time process control computers, the memory on those computers, the high-speed storage, was rotating magnetic drum memory. That drum could store about 50,000 bytes of data. And the data transfer rate was about 120,000 bytes per second. And because the drum was rotating, the place that you wanted on the drum was not always directly within reach. So you had to wait for the drum to average rotation to get around to the data that you wanted, which is about 60 milliseconds. And this motor plus the electronics was consuming about 1 kilowatt. That was a far better means of storing data than vacuum tubes. But we don't do that anymore. Nowadays, we have these things called USB thumb drives. And you can get a little tiny thumb drive that will store 2 terabytes of data. So you have a gigabyte, and then you have a terabyte. So thousands of bytes. And it can transfer data, not at like, a few 100,000 bytes per second. It can transfer data 550 million bytes per second. There's almost zero latency because there's no moving parts in it. It consumes less than 20 watts of power, not kilowatts, less than 20 watts at its peak. And you can buy one of these suckers on Amazon for under 200 bucks. So anytime you can create something that essentially performs the same role and it is financially a better model, the marketplace gravitates to that. And nowadays it does it quickly. I'm sure that there are some people that actually owned computers at one time that had rotating magnetic disk storage in it. But you go buy a computer nowadays, you go buy yourself a laptop or a tablet, there's no rotating media in them anymore because flash storage just got to be cheaper. The irony is flash storage makes use of electron quantum tunneling. So in summary, should we really be spending billions of dollars on quantum computer technology? At the moment, yes. But we should probably also be spending millions of dollars to come up with improved existing classical computer instruction sets and field programmable gate arrays that will do a lot of the quantumness, the quantumistic stuff. If we can do that and add that to the existing computers as an add-on, let's say something USB connected, then you're going to kind of kick the legs out from under the quantum computer marketplace. But for now, go ahead and spend the money. We'll advance some things, find out ways to make it less expensive to do the same capabilities. And then we'll eventually have, like we have GPUs and NPUs, we'll have a QPU, a quantum processing unit. But if you have any doubt that hardware technology and computers moves forward, I can remember back in the days when I was in high school, I worked on a computer that did not have an integer multiply and divide instruction. We implemented those suckers in software with shifts and rotates and adds and subtracts. Nowadays, you wouldn't want to own a computer if it couldn't do multiply and divide. In fact, you wouldn't want to own one that didn't have a floating point unit in it, built in. Well, I remember working with computers that had off-board floating point units. So it was a question of, is the software going to simulate the floating point unit faster if it's a simple enough instruction, or just send it out to the coprocessor and let it do it? Well, same thing is eventually going to be true with quantum processing units, because we're already seeing this with neural networks, that the NPUs are being added to the CPUs themselves. So once again, just be prepared for computing history to repeat itself again, and probably faster than it's done in the past. Lots of links. Several months worth of me looking at things. I especially like the quantum superposition explained without woo-woo. That was a fun watch. And then what a Toffoli gate is for people who go, what's a Toffoli gate? Is that like that chocolate? And then if you're not familiar with the additional instructions that computers have nowadays, the SIMD, these are the matrix and video manipulation instructions. They work in parallel. And some information on fuzzy logic. And then if you want to know about data storage on computers since 1985 and what rotating drum memory was all like, I actually worked on a computer driver interface for a rotating drum memory back in the day. And the oddball was, it was so much faster than the CPU was, even though it had a 60 millisecond lag time. It was so much faster if the data was right there that you had to enable the interrupt response routine before you actually sent the command to the drum, because it may be within one instruction time after you send the command that the data arrived, because the data was through a direct memory interface. So when the data started coming back from the drum, it would halt the processor to let the data flow into memory and then resume the processor. And there's your data. There was no lag time. And we actually had a bug in the operating system that the interrupt service routine crashed because it wasn't prepared to vector at the time that the IO was requested, and I went in and corrected that. Okay. There's only 40 slides, but lots of minutia. Comments? Questions? How many people have dug down into the rabbit hole of quantum computers that you might have a difference opinion? How many people knew that contemporary quantum computers required an MRI scale magnet to isolate the quantum computer from magnetic fields, like, I don't know, a truck driving by outside the building and the motor turning being a magnetic field pulse? Or, you don't think the ground is shaking, but the seismometers in California are going off all the time for very small microquakes. And those microquakes would actually destabilize the quantum bits inside the quantum computer. So whenever you see that giant cylinder and you see it's hung on this giant aluminum frame, look up in the top of the aluminum frame. In the aluminum frame, there are actually air bearings. That's where they have kind of a shiplap and they put compressed air in it. And then the quantum computer itself does not hang metal on metal. It hangs metal on compressed air on metal, because literally the micro earthquakes were destabilizing the quantum bits. If you had that kind of an Achilles heel with a regular computer, nobody would own one. Because it would say, when you put your laptop on the car seat and you drive down the road, all the memory in your computer would fail. Okay. I'm sure I'll get comments from the public audience once I put this out there on YouTube, but yeah. Okay, I'm going to stop recording.